Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammed Nabeel Abdur Rauf, and I'm here to do the video presentation on behalf of my team, Team 7. And our project is on the geometric PD controller design for the Robomaster EP core. And with me, I'm here on behalf of my teammates, Yussif Atta, Shajjad Dewan, and Mubarak Badamasi. Now, the Robomaster AP Core is a holonomic mobile robot with 4 mechanism wheels, and these wheels allow for omnidirectional movement. And it also has an integrated tooling manipulator, robotic arm manipulator, which actually has a gripper attached to it, and that allows for movement basically. The motivation of the project is basically to understand and implement geometric 3D controllers for mobile manipulators. In this case, we're dealing with the Robomaster EP core. And we plan to use this model-based approach for trajectory tracking and stabilization of the EP core. We plan to use, we employed Simscape multibody for the simulation and controller validation. The objectives of this project are as follows. We model the EP core robots in SolidWorks, simulate the kinematics and dynamics in MATLAB and Simscape, and design and test the PD controllers for the base and link motion under different scenarios. And now this is a cross-section of the Robomaster EP core replica. So due to the inaccessibility of the model card file itself, and after numerous contacts with the manufacturers and rejection, we basically built a similar robot from SolidWorks. Although we are not very we were not very experienced with SolidWorks, we had to learn. And this seems kind of amateur, but this is what we were able to come up with. And it's basically a replica of what we actually have in the EP core. We have the base, we have the wheels, we have the links, and we have the prismatic joints. Although the initial robot itself is holonomic, this model here is actually non-holonomic since we have some constraints that we've used. Now, due to some issues, we have the image on the left and the right have different axes. Initially, we imported into Simscape using the image on the left. But then after some issues that we faced due to orientation, we had to switch our axis. This is a Simscape model of the design AP core replica, and we have our end effector basically detached from it, but then we have our revolute joint and our planar joint. So it's exported and imported into Simscape multibody as an XML file, and we have our appropriate joint. The control strategy basically, since this is something that we're very new to as a group, we plan to take this progressively from the simplest case to the last case scenario that we're dealing with. And the initial stage or phase is to assume is to start with the free motion, assume the base of the EP core are fixed, and the joints basically swing under gravity. We have no control applied in this case scenario. Then the next case scenario is to assume a rectangular base motion for the base itself, and we model the base as a point mass, and we apply a geometric PD controller for in R3. But then in this case scenario, we're dealing with R3 instead of R3. We also move further by adding the rotational components, by converting or changing the rectangular joint for the base to a planar joint, and that allows for rotation about the Z. And in order to control such rotation, we also created a rotational basically controller for that basically. And then finally we have the full control of the links and the base together, and that gives us two phases or two types of control. We have the stabilization or set point regulation and trajectory tracking. Now, these are the controllers that we are actually implemented. For the base, for the translational motion, we have the geometric PD controller. For the rotational part of the base, we have this arrow that has been defined, and this is the appropriate controller. And also for the joint, we have these are the controller that we use for the joint. So in total, at the final stage, we actually have 3 controllers, 2 controllers for the base, 1 rotational and 1 translational, and then we have the controllers for the joint. So this is the full Simulink setup. Here we have the EP core that we use a subsystem we already showed initially. And here we have the controller for the base. Here we have the controller for the links. And here we define our trajectory, whether it's at a specific value. Both here is for the base, here is for the arm. And basically we have our feedback, we're feeding back the joint velocity and positions to the controller and feeding back the cleanup position and velocity into the base controllers. Now, this is the simulation for a free motion setup, where we see a lot of oscillations of the links. Of course, here like we mentioned, we assume that we're dealing with a fixed base. We can see that the links are actually moving, and the second link actually is oscillating more than the first link, as you can see here, but the velocities are going back and forth, as it's obvious from this simulation. Next, we have the case scenario where we assumed a rectangular joint, and for such a case scenario, we have no notation about the Z, but we can see here that we have some oscillations for the X, and this is reasonable. Why? Because we have the swinging of the arms, and the swinging of the arms causes the oscillation not to die out quickly. And we can also see the velocities. It goes to 0, but then for the X, we have a lot of oscillations. Now, next, we move to the planar joint without control of links. So we switch basically to a planar joint, and we put our set points to be 1 for both our X and Y, and we can see that it's actually following the trajectory quite nicely. And for our rotation to be minus pi/2. So we have some deviation from what you actually set it to be. And these are control torques, and these are velocities. And we can see oscillations of the links here in D, and that is because we've not started controlling the links. Now we move to the results for controlling the links themselves. So in this case scenario, we are controlling the links and the base at the same time. Now, in this case scenario, we basically simply just accounted for gravity and tried to compensate for it, such that the links actually they start at a particular point. And of course, it might not be as perfect as we want it to be, but due to our calculation of the gravity aspects, vector or covector, but we have something close to what we want. And basically for this is the simulation for our base. We can see that we have no overshoot. The settling time is quite fast. Steady state error is null, and we can only observe some deviations for around the Z as some steady state error. And with the velocities of force go to 0, and these are observed torques. Now, of course, this is using a specific set of Kp and Kd values for the controller. So these are the values that we used here. So we can see here that the ratio of Kp to Kd is actually 1. So that's why we're having no overshoots, and we are not having something that is overdamped. So it's not underdamped and it's not overdamped, right? Now, for our links, we also have some deviation from what we want, like we can see here. So it's not perfectly how we want it to be because of the compensation we've had for our gravity entity. We can see some steady state errors, but it basically stays at that particular point. And this is basically for the first set of values. Now, for the second set of values here, let's come here. We can see that the ratio of our Kp to Kd is actually more than 2. And that means we are having the damping, which is supposed to be the job of the Kd, is not as much. So that's why we are having this kind of motion where we have some overshoot here. So we have an underdamped system. Now, both our X and Y actually follow the same logic. And if we see our robot here, we can see that it's actually oscillating before it stops. Now, this can also be seen in the oscillation can also be seen in our velocities and also in our torques as the controllers try to cause the robot to stop. Now we have for the links, we have similar simulations or output. We have our velocities going to 0, but we have the steady state error to be of equal magnitude as is in the former case scenario. Now we move, we've just described the set points to regularization or stabilization for both the base and the links. Now we are looking at tracking for both the base and the links. For tracking, we have here that using the first set of values that we've just displayed, we can see that initially there are some sort of deviation, but then the controller quickly corrects the base and allows it to follow the path that has been set for it. And this is a combination of sine and cosine, which is a circular path. And we can observe our steady state error in terms of the rotation or the orientation or the angle displacement that we have about said. And of course, if we have our position trajectory to be trigonometric, our velocities would also be trigonometric. And we can see here, same case scenario, you can see some form of correction happening after a period of time, but it does not take as long. And we've also seen here in our control talk, you can see this point of deep here. This is something that will be discussed later, especially as this pertains actually to the rotation itself. Now, this is the trajectory path for the links themselves. So they're supposed, after a period of 20 seconds, they're supposed to gradually increase and extend outwards, and also reduce after 40 seconds. We can see that the steady state error that has been observed from the beginning is basically the starting point for both links. But in terms of trajectory tracking, it tracks it, but then with the same steady state error. Now, in terms of the velocity, you can see a sudden spike in velocity here, and it goes until it gets to the point where it changes its direction. So it's kind of sudden. It might not necessarily be something that actuators can actually implement in real life. Although, if we look at the control efforts being used here, it's actually not much. So in theory, we shouldn't really have that much problem. We just don't know if we can have such an instantaneous response in real life. Now, this is basically the simulation. So we can see it following the circular path. That is the base following the circular path. Now, the idea is after a period of time, the links also start following a specific trajectory that has been set for them, and it extends outwards, then comes back inwards. So this is what we are observing here. It's extending outwards gradually over time. Then after a period of time, after it reaches a particular angle, then it comes back inwards. So of course, this is using a specific value for our gains, the controller gains. So this basically continues, circular motion continues to the simulation stops. Now this is using the second set of gain values, and here we can see that the correction actually happens much later. It seems to happen much later, and this the hypothesis is that this is due to the lower gain that we have for this for the second set. And but apart from that, after it corrects itself, we see it following the circular path without any issues. So this correction can actually also be seen from the velocity. We can see that the velocity also we have some wiggling here, but then it only corrects itself after a period of time. Now, just like we see, if we observe from the former simulation, and it's also the same for the new one, we have this peak point here at 30. So that basically affects, in both cases of the gains, it affects actually the torque. So when it gets to the 30, we can see the torque dipping, and it goes back to its former value. Now here for the link joints, we can see that we have a smoother transition compared to the first one. And that's also again because of the gain values that we have. The first one had higher gains, so it was more aggressive. This one has lower gains, so it was smoother. And this smooth nature is actually more obvious when we look at the velocity here, the angular velocity, where we see a gradual increase to this point, and we see a gradual reduction. And that's basically in contrast to here, where we have like a sharp increase and sharp reduction. So we observe something similar too. We can see that starting from 20, there seems to be an obvious deviation until we get to 30. And at that point of 30, there's a convergence at the 0. You basically have no torque happening there. And then it comes back with some steady state value. So generally, it was quite a challenging task and project for us because we were not very familiar with the softwares that we actually used. We had to do a lot of things from scratch for ourselves. Building the model from SolidWorks took a lot of time because we were novices to some of this software. Then after building the model, we also had like importing into Simscape multibody, aligning it well. We had a lot of issues with that. Initially, it was not being aligned the right way, and we had the robot falling off. Then after that, we also had implementing the controllers were not very direct. We had to do a lot of trial and errors, but we worked together as a team, and we were able to learn a lot. It might not be exceptional, but it was honest work, and we are actually very proud of ourselves. And we were able to basically implement what we were being taught in the class practically and actually see the effect. And again, even though we had like a decoupled system, we could actually see that, of course, with some constraints, we could see that the controllers actually performed not so bad. Now, in conclusion, we're able to implement the PD control successfully to basically it's not what we have is non-holonomic, but then it basically behaves like a holonomic manipulator. It was able to track, although with some steady state error for the orientations, but for the translations, with no steady state error and very fast settling time. And these, of course, reinforce a lot of concept that we learned in the class in terms of control. And to extend this project, we could also extend it to some form of interaction control or look for robust control methods. And of course, since we implemented the controllers in a decoupled manner, the ideal case scenario would be to implement the controllers using SE3 or SE2. And of course, in the best case scenario, we integrate this with Rust2 for real-time implementation. And with that, we'd be able to control possibly the robot. Thank you. These are the attached links, the demo, and thank you.